Hi class, it's me, Mr. Morris, and we're going to do a video on atomic mass of an element. I want you guys to know how to calculate atomic mass by the end of this video, but I also want you to know what it is. So let's get started out talking about the video that Mr. B did with the beans. So he started out and he made this video with some red beans and some white beans. So if you'll remember, the red beans represented protons, the white beans represented neutrons, and we kind of just ignore the electrons right now because we're not dealing with them just yet. Okay, so he had 9 beans in each case. So each of the bags had 9 red beans, which is the protons. The first type of bag had 10 neutrons. The second type had 8 neutrons, and the third type had 11 neutrons. You wouldn't remember this from the video probably, but I'm just reminding you of kind of what it was. Then we added those together to find out what the mass number was. That was the total number of beans. So 9 plus 10 gives us a mass number of 19. 9 plus 8 gives us a mass number of 17. And 9 plus 11 gives us a mass number of 20. So just a reminder of how we find that, and then we would write the isotope name. Now, to find the name of the element, we've got to look at the periodic table and compare the number of protons to the atomic number. Remember, the number of protons is the atomic number. So if we could just find an element with an atomic number of 9, that's what we've got here. So I'm going to scoot over. I've got a periodic table right here. I know it's kind of flipped over sideways, but you can see that fluorine has an atomic number of 9. So we can assume that we've got fluorine here. So I can write that as the name. And when you're writing an isotope name, you're going to put a dash and then you put your mass number afterward. So fluorine 19 is the isotope of fluorine that has a mass of 19. Fluorine 17 is the one with a mass of 17 AMU. And then fluorine 20 is the one that has 11 neutrons, and therefore it's got a mass number of 20. All right, then he talked about the frequency of appearance. Again, this is something you probably don't have right in front of you right now, but if you were to look at it, he had 25 bags that represented fluorine 19. He had 2 bags that represented fluorine 17, and he had only 1 bag that represented fluorine 20. So what were the total number of bags? Well, I could add those up. 25 plus 2 plus 1 gives us 28. And then I could find the fractional abundance. That means I'm just going to make a fraction of the number of bags of each type divided by the total number of bags. So 25 out of 28 of the bags were fluorine 19. 2 of the 28 were fluorine 17. We could simplify that if we wanted to, but I don't really care to right now. So I know it was 1 over 14, but all right, 1 over 28, 1 out of 28 was fluorine 20. So if I wanted to find out what that was as like a percentage, the first thing you would do is solve that fraction, put that in a calculator. If you do 25 divided by 28, you're going to get a decimal answer. You could turn it into a percentage, but right now we just want to write the abundance as a decimal. So 25 divided by 28 would give you 0.8929. If I just want to keep 4 significant figures, and that's what I want to do right now. Don't worry about the sig figs here. This is just kind of the way I'm doing this. Okay. 2 over 28, 0.07143. That is a 7. There. Okay. And then 1 over 28 gives us 0.03571. or that's a 7. All right. So if I were to ask you to tell me the average number of beans in each bag, what you'd have to do is add up all of the beans and then divide by the number of bags. Well, we have our total number of bags up here as 28. So I'm going to divide by 28, but then I would have to add up all the beans. Well, 25 of them had 19 beans. 2 of them had 17 beans, and then 1 of them had 20 beans. So I could add those up. So I'd do 20 plus 17 plus 17, because there's 2 of those, plus 19 25 times. Sounds like a little too much work. So what I would do is 19 times 25. 25 19 times. That's going to give me the total number of beans from the ones that had a mass number of 19. Plus, and then we're going to do 17 times 2 plus 20 times 1 equals, when you add that all up, you are going to get 529. If you just put that in a calculator, you'll get 529. That's the total mass of all of them together. If I want to know the average, if I wanted to know the average mass, I would do that number, 529, divided by the number of bags, which is 28. It's the same way you find an average usually. You add up all the things you have, and then you divide by the number of sets. We're dividing by number of bags, and we end up with 18.9 if you put that in a calculator. And our units are AMU. But I've got 18.9. That's one way of doing it. The problem is I can't count atoms, and I can't count protons and neutrons. So what we need to do is learn a different way to do it, to do an average, a weighted average like this, using the abundance. And I'm just going to show you that you'll get the same answer. Okay, so I'm going to switch colors here. I'm going to use the abundance. I'm going to do abundance multiplied by mass for each of these isotopes. And then I'm going to add them together. So the way this works is we're going to put the mass, which is 19, times 0.8929 times the abundance, plus the other mass. The next mass is 17. This one here. So I just did 19 times 0.8929. Now I'm doing 17 times 0.07143. Plus 20 times 0.03571. If you were to put this in a calculator, multiply 19 times 0.8929 plus 17 times 0.07143 plus 20 times 0.03571, the answer you get is 18.9, which is the same thing that we got before. Now I know that you're probably going, well, why would I do that? I can find the answer the other way. Well, the situation is this is the only way to find an average of all of the mass numbers in a sample. which is what we're going to be doing. That's what the average atomic mass is. And when you look on the periodic table, those atomic masses, that's what they are. They're the average atomic mass. So we want to go through a definition, and then we're going to go through some practice problems as well. And we will be using a method very similar to what we just did here over and over again. Don't worry, we'll do a lot of practice problems, but this is a method you need to make sure you know how to do. All right, the average atomic mass of an element is the weighted average mass of the isotopes of that element. So all of the isotopes of an element, the average of all of their masses, that's what average atomic mass is. So since we can't weigh individual atoms, we use these instruments called mass spectrometers. This is not a vocab quiz type thing you need to know. I'm just giving you a glimpse of college and AP chemistry and something that we would use, okay? So we would use a mass spectrometer to find the mass of the different elements, the different isotopes. And it's also going to tell us the percent of each type of isotope that we get. It would give you a mass spectrum, which is like a graph. And the graph tells us a number of things. So down here on the bottom, it says the relative mass. So this peak, the first peak, is a mass of 10. And the second peak has a mass of right between 10 and 12. So I would say the second peak has a mass of about 11, right? The percent abundance is the y-axis. So about 20% of all of boron has a mass of 10, and about 80% of all of the boron atoms have a mass of 11. That's what this graph tells us. Now here's a visual representation of the same thing. Boron 10, the boron 10 nucleus, and we could count these. The red ones are going to represent protons. Those are positive. I have 1, 2, 3, 4, 5 protons. By the way, if you wanted to confirm that that is actually boron, we could look for the element with 5 protons. Boron has 5 protons, okay. And this over here is also boron because it has the same number of protons. So what's different between them? Well, this one has 1, 2, 3, 4, 5 neutrons, which gives it a mass of 10. This one has 1, 2, 3, 4, 5, 6 neutrons. So your protons plus neutrons would give you a mass of 11. And if I wanted to find their average mass, we're going to use the same method we used above. 20% or 0.20 comes from boron 10, and 80% or 0.80 comes from boron 11. So if I wanted to know the average atomic mass, the way I would do that is by putting, and I'm just going to zoom out a little bit, I would put 0.20 times 10 plus 0.80 times 11. So that's our formula. That's basically how it works. It's your percent turned into a decimal times the mass plus the other percent turned into a decimal times the mass. When you add that up, you're going to get 10.8 AMU. You could confirm that that is correct by checking boron and seeing if that's really close to the same mass. Boron has a mass of 10.812, so 10.8 is very close to the same mass. All right, so the summary of that example we just went through. The mass number is the number of protons plus the number of neutrons. Make sure that you know that. The average atomic mass is not the same thing. Make sure you know this. It is the weighted average mass number of all of the isotopes of an element. So you have to know the percentage and you have to know the mass of your isotopes. You cannot use the basic average formula for this because there are different amounts of each isotope. That's why we have to use a weighted average. Note, the average atomic mass is usually closest to the mass of the most abundant isotope, so the one with the greater percent. So that would make sense. 10.8 is closer to 11 than to 10, and the reason is because we have a greater percentage of it, okay? So I'm going to undo those marks on there, but a greater percentage means it's more abundant, and your mass should be closer to that mass. The average mass should be closer to the mass of that isotope. And here is our formula that just kind of sums up what we've talked about. The atomic mass is the abundance of the first isotope times the mass of the first isotope plus the abundance of the second isotope times the mass of the second isotope, plus we could do the same thing with the third. Abundance of the third isotope times the mass of the third isotope, and you could keep going with as many isotopes as you've got. And down here we've got just a different way of looking at solving this same type of problem. You can use whichever method makes the most sense to you. We will be using in pre-AP chemistry, we will be using that equation for something else later, so you need to be aware of it, that atomic mass is abundance times mass plus abundance times mass plus abundance times mass. But if this way of thinking through it makes more sense to you, you can use it more often than not, okay? You can multiply each exact mass by its abundance. When I say exact mass, I mean if I give you the mass with decimal points, you want to use that instead of just assuming that it's really close to a whole number, okay? And then turn your abundance into a decimal. So we're just going to move the decimal 2 places or divide by 100. It means the same thing, okay? But it's always 2 spaces. In this case, it's 0.0463, 0.0310. And we're going to multiply those numbers by each other. So 27.9769 times 0.9223, get an answer. 28.9765 times 0.0467, and we'll get an answer out there. And then 29.9738 times 0.0310, put an answer right there, and then we will add those together. So when you crunch those numbers in the calculator, what you get here is 25.80, rounding to 4 sig figs. And then this one's going to be 3 sig figs. I get 1.35. This one is 3 sig figs, and I would get 0.929. All right, so we multiplied each of them, abundance times mass, and abundance times mass. Now we're just going to add those answers together. Now, this is a good chance to remind you that when we're adding or subtracting, we want to round to the lowest number of decimal places. So the lowest number of decimal places that I have here is 2 decimal places, and it's right there. So I'm going to round to that place. When I add it up in my calculator, it's going to round up to 28.08. I think it's 28.079, but that rounds up to 28.08 since I'm rounding where I drew that dotted line. And our units are AMU. We just want our units to match what we have right there. All right, last thing we want to do here is it says to identify the element. So let's look at that atomic mass, 28.08, and let's see what element that is the closest to. Remember, atomic mass is that number at the bottom, so let's see. I've got 24 for magnesium, 26.9. Okay, 28.086 is silicon. So I think that this is probably silicon. And I can make that assumption based on the atomic mass. All right, you can pause the video, try the next one on your own, check your answer, and as long as you get the same answer as me, you don't need to watch the whole video. But if you don't, then you might want to slow it down, watch the next example with me as I work through it. All right, last example problem. We have 12.0000 AMU and 98.90%. We're going to change that percent into a decimal, so it's 0.9890. All right, I'm going to move the decimal twice here, and I have 0.0110. I'm just going to rewrite these actually to be a little more clear with what we're doing. 12.0000 times 0.9890, and then I have 13.0034 times 0.0110. Let's find out what the calculator says. When you punch that in, you should get 11.87 if we're rounding to 4 sig figs. And I want 3 sig figs in this case. My answer is going to be 0.143. We'll add those together. Again, round to the lowest number of decimal places because this is an addition or a subtraction problem. It's an addition problem. I get 12.01 AMU. And what element would that be? 12.01 AMU. Let's look. Looks like it's about the same mass as carbon, 12.01. 12.011. So this is carbon. All right, and by the way, you can kind of check your work and make sure that it makes sense. Since 98% of my isotope of the sample was isotope 1, my atomic mass, my average atomic mass, should be really close to that mass. And it is. It's 12.01 instead of 12, right? Up here, my average atomic mass should be really the closest to isotope 1 again, because isotope 1 has 92%. Well, that's about 28, and this is really close to 28. So it's a good way to check your work. So try your hand at a few of the practice problems and be ready for the next video.